Okay, so the next thing that we have here is basically the next part in the text that we have here is called physical quantities and units. And this is, of course, an important part of physics, meaning that in this part of the text you learn how to measure length, how to measure mass, how to measure time, how to measure electric current, how to measure luminous intensity, and so on and so forth. There is around some 7 base units, and then or 7 base physical quantities, and there is 7 base units for them. And then using those base units you learn how to measure something, how to express that measurement in the unit that accompanies that physical quantity. And there is also some notation that you need to understand, otherwise your physics will be mixed up. You will write your physics in such a way that people will not understand. So this part is just like a foundation for the whole journey of physics that you want to take. So here we have a picture that says that the distance from the Earth to the Moon may seem immense, but it's just a tiny fraction of the distance from Earth to other celestial bodies. I don't know why they have basically included this picture here, but that's what it is. And so the range of objects and phenomena studied in physics is immense, from the incredibly short lifetime of a nucleus to the age of the Earth, from the tiny sizes of subnuclear particles to the vast distance to the edges of the known universe, from the force exerted by a jumping flea to the force between Earth and Sun. There are enough factors of 10 to challenge the imagination of even the most experienced scientist. Giving numerical values for physical quantities and equations for physical principles allows us to understand nature much more deeply than does qualitative description alone. To comprehend these vast ranges, we must also have accepted units in which to express them. And we shall find that even in the potentially mundane discussion of meters, kilograms, and seconds, a profound simplicity of nature appears. All physical quantities can be expressed as combinations of only 4 fundamental physical quantities: length, mass, time, and electric current. So in this text it seems that the base units are 4, or at least 4 now. All physical quantities can be expressed as combinations of only 4 fundamental physical quantities: length, mass, time, and electric current. So that means that basically if you have 4 fundamental physical quantities, if you understand 4 fundamental physical quantities, as which are basically the length, which are basically length, mass, time and electric current, then all the other physical quantities can be expressed in terms of these basically fundamental physical quantities, or using these basically 4 fundamental physical quantities, meaning that, for example, force will be a combination of length, mass, and, for example, I think force is mass times acceleration. So for example, that would be mass and so for example, let me give you an example. You know that F is equal to ma, for example. That is force. That is basically mass. That is acceleration. That is acceleration. Acceleration. Right? Now, acceleration in physics is the basically is the rate of change of speed, right? So acceleration is nothing but the rate of change of speed. So that means that if I know something about speed, so speed is basically, and speed is nothing but distance by time. Meaning that, for example, if you want to know how fast an object is moving, then, for example, let's say that an object is moving along a straight line. The object starts its motion at this point, and then it stops at this point. Or at least we studied the motion between these 2 points, between these two points. So over here, if I know, for example, what was the time when I started measuring the motion, which is t1, for example, and if I know, for example, what was the time when the motion stopped, or when I stopped observing the motion, so let's call that t2, and let's call this, for example, position 1 p1, and let's call this position 1 p2, right? So the distance that the object has taken, has covered in this time distance, is basically, in this time interval, is basically p2 minus p1. If I take this point as 0, for example, as 0 of the coordinate system, or whatever, however you want to consider that, then there is some distance between the point p1 and p2. If you find that distance and divided by the time that it takes the object to get from t1 to t2, then you will get the speed, meaning that you can say that the speed is the rate of change of position, right? So the rate of change of position is speed, and the rate of change of speed is acceleration. So then it makes sense that, for example, and we have distance is nothing but length, right? This is nothing but length, and this is of course time. Now, since we are talking about acceleration, so then acceleration, since it is the rate of change of speed, then acceleration becomes distance by time. And since we are talking about the rate of change of this, then you divide that by time. This becomes acceleration, or you can use this to calculate acceleration of an object, meaning that the rate of change of distance, right? Or the rate of change of position. There is the rate of change of is basically 2 times in my statement. Or if you are basically familiar with calculus, you can call this, for example, the rate of change of, for example, distance, you can call it d by dx of, for example, p of x, d by dx of p of x, and which is basically stands for basically position. And if you take the d by dx of this, d by dx of d by dx of p of x, meaning that the d by dx of p of x calculates the rate of change of position. And then again, if you calculate the rate of change of this whole thing, then that means that you have gotten your acceleration. But of course, this is the course that we are doing here is an algebra based course, so you don't really need to bother about calculus here. So at the end of the day, what that means is that basically then, for example, force that we are talking about here, we need a way to express it in terms of the units that we have, or the units that we have. So the units that we have for acceleration, I need the unit for length, and also the unit for time, and the unit for time. And then mass, basically the unit for mass, also we have it basically among these 4 units. So then I can say that basically then force is the same thing as the unit for mass is kilogram in the system that we use. And basically we use the SI system of units. In the SI system of units, the unit for mass is kilogram. Now the unit for distance is meter. So you have meter. The unit for time is seconds. The unit for time is second. So you have basically so you have kilogram times mass. So this gives you basically kilogram times mass divided by second, right? And that is the same thing as kilogram times mass divided by second squared. And some people write this as kilogram mass and then second raised to the power -2. And that becomes basically how you, and that is how you, for example, express force in terms of the 4 fundamental physical quantities that we have. So as you can see, any sort of course, there is actually 7 of them. There is the length, there is the mass, there is the time, there is electric current, there is also luminous intensity, there is electric charge, there is so that is 6, and there is 1 more. But we basically, based on what we are doing here in this part of the text, we do not actually need those 3 units yet. Once we use them, then we will introduce them in the text. So for now, you can just simply assume that there is only 4 fundamental physical quantities for length, for mass, for time, and for electric current. And anything that you might come across for now in the text, they can be in the same manner expressed in terms of these 4 physical quantities, which in turn means that any sort of physical quantity can be expressed, which means that basically you will be able to talk about any sort of physical quantity without any problems, in such a way that everybody will understand you without confusion or ambiguity, right? So that's basically this part. Now we define a physical quantity either by specifying how it is measured or by stating how it is calculated from other measurements. For example, we define distance and time by specifying methods for measuring them, whereas we define average speed by stating that it is calculated as distance traveled divided by time of travel, right? So the base quantities that we have, meaning that, for example, distance and time, or length and time. Length is basically, for example, the new definition for length is the meter. The name of the unit is the meter, and the unit for that is the meter, and the symbol for that is lowercase m, right? That is for length. That is used for length. Now, in the case of length, the way that we define the physical quantity is how it is measured, or we specify it by saying how it is basically measured. The most updated definition of the unit for the physical quantity length is basically, for example, that is basically based on the unit time, meaning that, for example, we say that 1 meter is the distance that light travels in a vacuum, for example, in a time interval of 1 divided by approximately 300 million seconds. 1 divided by 300 million seconds. So basically then you can say that 1 meter is the distance traveled by light in vacuum in a time interval of, for example, 1 divided by approximately 300 million seconds. So as you can see then this is how we measure this physical quantity, and that happens to be based on another definition, and that definition happens to be time here. Meaning that first you need to understand what is 1 second, and then based on that you can understand what is 1 meter. And the interesting thing about these units is that, for example, you see 1 meter is the distance traveled by light in vacuum in a time interval of so many seconds. So this is something that can never change. Nobody can change that. Nobody has any sort of influence over that. And the speed of light, of course, is never going to change. It has never changed as far as we know. So this unit is something that you can absolutely rely on. But if you say that, for example, 1 meter is the distance between the tip of my, one particular finger of mine all the way up to my elbow, for example, then everybody should have access to my elbow and to my hand, to my arm, basically, which is not possible. Or if I say that the meter is basically the measurement that you can make across my rug on my floor, then everybody should have access to my rug, which is not possible. And moreover, my rug does change its length under different conditions over time, and so this is not reliable. So for those kinds of reasons, we do not rely on those kinds of units, and so we have come up with basically this definition, which is primarily based on the definition of second. And then the definition of second happens to be, for example, a certain number of radiations of a cesium-133 atom, for example, which is again something that everybody can have access to wherever they happen to be in the world. And then now they have made, scientists have made these CCM clocks that are accurate to something about 1 microsecond in a year or so. So it's actually very, very, very accurate, right? So that's basically how we do this sort of thing. So here it says that we define a physical quantity either by specifying how it's measured, or by stating how it's calculated from other measurements. For example, we define distance and time by specifying methods for measuring them, which I just talked about. Whereas we define average speed by stating that it is calculated as distance traveled divided by the time of travel, right? And we talked about both of these already. So measurements of physical quantities are expressed in terms of units, which are standardized values. For example, the length of a race, which is a physical quantity, can be expressed in units of meters for sprinters, or kilometers for distance runners, right? So without standardized units, it would be extremely difficult for scientists to express and compare measured values in a meaningful way. So for example, over here, this person is reading a map, and the map basically has provided him with a scale that says that this distance on the map is 1 cable. And so then you need to basically you need to put this scale across the path and see how many such distances you can find across this line, and then across the line connecting the 2 points. And then you can say that, for example, this is 1, 2, 3, 4, 5, 6, 7, 8, and for example, that if you start from X and go to Y down here on the bottom of the map, then the distance is going to be 9 cable, and depending on your speed, it's going to take you so many, for example, hours or so many days to get there. So, but now the scale here is in terms of a unit, which is something that he doesn't understand, meaning that, for example, 1 cable might be something that some people might understand in some specific part of the world. For example, suppose you go to Africa and people have made up some unit, arbitrary unit for themselves, and they understand it. Everybody knows, for example, 1 cable is this much length, and everybody knows everything about it. But then if you give this map to somebody outside of Africa, then people will be confused, right? So, and for the same reason, these units have to be standardized units, meaning in such a way that everybody understands them. So there are 2 major systems of units used in the world: the SI unit, also known as the metric system, and the English units, also known as the customary or the imperial system. English units were historically used in nations once ruled by the British Empire and are still widely used in the United States. Virtually every other country in the world now uses SI units as the standard. The metric system is also the standard system agreed upon by scientists and mathematicians. The acronym SI is derived from the French Système International, something like that, which is basically, the name is there because the organization that deals with all of these standardization of units and everything is some organization, at least in France. I don't know if it's originally French or anything, but it most probably happens to be in France. So that's basically but again, I'm not sure about this statement, so I know that there is some organization in France that is a prominent one dealing with all of these standardization and all of such matters, but I don't know much about that actually. So basically then what we have here is that so then we have two major systems of units. We have two major systems of units which in the world, which is the SI units and which is also known as the metric system, right? And we also have the English units. Or basically also known as the customary or imperial system. Also known as the customary or imperial system. Imperial system. So so then basically what we have here is basically we have these two major systems of units in the world, the SI units, which is also known as the metric system, and it's known as the metric system because it is based on the metric system. The metric system is a much older system that was being used in the world, and then they have made some changes to the metric system, and then out of the metric system they have made the SI units, or you can say that the SI units are, the SI system is some sort of variation, or not exactly variation, but some sort of improvement upon the metric system. But it's basically the exact same system. And the English units are basically, which is also known as the customary or imperial system, is the unit that was kind of, well, historically it was used because of the British Empire, and the British Empire, and the fact that the British Empire was ruling, I mean, in the past the British Empire was ruling many countries in the world, which is for most parts of the world not the case anymore, and so when the British, and when that happens, basically when you rule a country, then your language becomes the language of that country, and all of your standards become the standards of that country. And so for that reason, basically then the English units have been introduced all over the world, almost all over the world, and it was being used all over the world until the SI units came to be. So this is called also the customary or the imperial system. Now so that is that basically. Now the units over here are a little bit, there is a system over here which is called I think this system is called the FPS system, foot-pound second, or there is another system as well which is kilogram. There is, let me tell you about this system here. There is FPS and MKS. So, and CGS, and there is also CGS. So it says that the base units for length, mass, and time in these systems are as follows. So you have basically the CGS system. In the CGS system, you have centimeter, you have the centimeter, you have the gram. This is for mass, this is for length, and S for second. That is the CGS system. Now there is this MKS system as well. There is the MKS system as well, which is meter, kilogram, second. This is the meter is the unit for length. K is kilogram for mass. Kilogram for mass. And second is the unit for time. And there is another system here also, which is FPS. And the FPS system is foot, pound, and second. Foot, pound, and second. Okay. So these are these three systems. Now in the SI system, basically the unit for the length is meter. The unit for the mass is kilogram, and the unit for time is second. Meter, kilogram, second. I think this is the metric system, if I'm not mistaken. I think this is the metric system. And that is basically that. Okay, so now let's move on to SI units, fundamental and derived units. Okay, so the next thing that we have here is fundamental and derived units. And so table 1.1, which is this table over here, gives the fundamental SI units that are used throughout this textbook. This text uses non-SI units for a few applications where they are very common use, such as the measurement of blood pressure in millimeters of mercury. Whenever non-SI units are discussed, they will be tied to SI units through conversion. So that's basically that. So the fundamental SI units for length is the meter, for mass is the kilogram, for the time is the second, and for the electric current is ampere. And it's important to pay attention to the fact that basically the fundamental SI units for, as you can see here, for example, for length. For length, you have the fundamental SI units, and for length you have, for example, the name of the unit is basically the meter, right? So you can see that meter is written as M-E-T-E-R, with a lowercase m here and everything lowercase. Now there is also the meter is also written this way as well, M-I-T-R-E, which is mainly British English and used in India as well. But this textbook is American, and the way that I understand that I can write English is that I can write in English is everything is based on American English, so I don't write in British English, so I use always this type of writing the language. But doesn't really matter whether you write it as meter or basically, or whether you write it this way, it is correct. But now this is the unit name, and the symbol for unit is a lowercase m. This is the lowercase m, and that is important, meaning that, for example, you cannot mix it up with, instead of m, you cannot write a m like this, because this kind of m would have some other meaning in physics, and then you would get confused, other people would get confused. The symbol for this unit is a lowercase m. Now, talking about mass, the name of the unit is the kilogram. And all one word, basically, and no spaces. And the symbol for the unit is kg, or lowercase k, lowercase g. That is basically the unit for mass. The unit for time is basically the second. The unit for time is the second, and again lowercase s, and so on and so forth, and lowercase s as the symbol of the unit. The unit for electric current, is basically ampere, which is the name of a scientist, and for the same reason the unit symbol has become an uppercase A. This is done usually in physics in the case of units that are adopted after scientist names. For example, there is ohm, and there is all kinds of course, all science. I mean, physics has been created by scientists, of course. But sometimes the names are not used. Whenever the name is used, then basically the symbol of the unit is capitalized. So you basically, important is that this notation, you're consistent with this notation all across your life in physics, basically. That's the important part. Now, it's intriguing. It's an intriguing fact that some physical quantities are more fundamental than others, and that the most fundamental physical quantities can be defined only in terms of the procedures used to measure them. So for example, in the text we talked about how we measure length, or how we measure time. So for example, for time we use something in nature, and that thing in nature is the cesium-133 atom. Cesium-133 atom has these vibrations, and these vibrations are, it seems that you're supposed to, I don't know, somehow you have to excite it or do something to the cesium atom. I'm not really sure what they do to that, or if it does that sort of, if it basically has those sorts of vibrations naturally. I am not sure about that. But whatever the case is, basically it seems that these vibrations can be measured, and then a certain number of those vibrations are basically measured as, for example, 1 second. So that is an example of basically those units that can be measured only in terms of the procedures in which the procedures used in order to measure those units, basically. So to repeat this, in case you didn't understand my sentence, I said that the units in which they are measured are It's an intriguing fact that some physical quantities are more fundamental than others, and that the most fundamental physical quantities can be defined only in terms of the procedures used to measure them. You can take the example of, for example, length or time. Mass is not much about procedures or anything. For mass, we have a mass at some museum in France, and that becomes basically every other unit of mass is compared against that mass which is kept as at the museum. They haven't still come up with a good way to measure mass in a different way, in such a way that the unit is more reliable. Because the problem with this kind of definition is that mass over time, of course, will have over time that mass at the museum, no matter how you keep it intact and nothing touches it, even not air touches it, it could degrade, and the mass of that cylinder is going to change, of course. Even by 10 raised to power, for example, -6 of a kilogram, it's going to change anyway. But it seems that still science is not able to, for example, is not able to measure the mass of atoms, for example, reliably. So they're not doing that. So that's basically about mass. And about the electric current, still the method is a little bit crude, meaning that you have to make certain assumptions that you have a length of, basically an infinite length of wire of cross section that can be neglected, and then there is a force between, if there is such and such force between those two wires in vacuum, then in each of those wires a current of, for example, 1 ampere is flowing, which is, the method is not very good. But well, that's basically how it is for now. Now, in this textbook, the fundamental physical quantities are taken to be length, mass, time, and electric current. Note that electric current will not be introduced until much later in this text. All other physical quantities, such as force and electric charge, can be expressed as algebraic combinations of length, mass, time, and current. For example, speed is length divided by time. These units are called derived units. So we have the fundamental units, which we have 4 of them. We have, or actually these are not units, these are physical quantities. So basically length, mass, time, and electric current, these are fundamental physical quantities. And there is also the derived physical quantities, which are the physical quantities that are measured in terms of the fundamental quantities. For example, speed, or for example, or acceleration, or force, and that sort of thing, right? So that is that. And then the units of time, length, and mass, the second, meter, and kilogram. So the second, the SI unit for time, the second, or abbreviated S, has a long history. For many years it was defined as 1 divided by 86,400 of a mean solar day. More recently, a new standard was adopted to gain greater accuracy and to define the second in terms of a non-varying or constant physical phenomenon, because the solar day is getting longer due to very gradual slowing of the Earth's rotation. So cesium atoms can be made to vibrate in a very steady way. This is what I was talking about. Cesium atoms can be made to vibrate in a very steady way, and these vibrations can be readily observed and counted. In 1967, the second was redefined as the time required for basically for 9 million, that's 9,192,631,770 of these vibrations. Accuracy in the fundamental units is essential because all measurements are ultimately expressed in terms of fundamental units, and that can be no more accurate than are the fundamental units themselves, right? And this is a cesium clock. This photograph has been taken from the top of a tower in which a long tower in which basically the clock has been installed. So it's an atomic clock such as this one uses the vibrations of cesium atoms to keep time to a precision of better than a microsecond per year. I was wrong about what I said about the accuracy. The accuracy is better than a microsecond per year, not a day, a year. The fundamental unit of time, the second, is based on such clocks. This image is looking down from the top of an atomic fountain nearly 30 feet tall. 30 feet would be something about, I think, I'm not very good at the customary system. 30 feet is something about 900 meters or so. I'm not sure. So if you want to convert, of course, in a physics course, it's not a good idea to use Google, but for now, foot to meter, for example. So you see 1 foot is equal to 0.3048 meters, and 30 feet would be 9 meters. About 10 meters is about 10 meters is the height of this tower. Now, the meter, the SI unit for length is the meter, abbreviated as M. Its definition has also changed over time to become more accurate and precise. The meter was first defined in 1791 as 1 divided by 10 million of the distance from the equator to the North Pole. So 1 divided by 2, meaning that you take the distance from the equator to the North Pole divided by 10 million, and that becomes 1 meter. That was defined in 1791. Then this measurement was improved in 1889 by redefining the meter to be the distance between two engraved lines on a platinum iridium bar now kept near Paris. In 1960, it had become possible to define the meter even more accurately in terms of the wavelength of light, so it was again redefined as 1,657,63.73 wavelengths of orange light emitted by krypton atoms. In 1983, the meter was given its present definition partly for greater accuracy, as the distance light travels in vacuum in 1 divided by 299,792,458 of a second. And so this is the current definition, which was basically defined in 1983. So it's the distance light travels in vacuum in 1 divided by basically approximately 300 millionths of a 1/300 millionth of a second. And this change defines the speed of light to be exactly 299,792,458 meters per second, right? The length of the meter will change if the speed of light is someday measured with greater accuracy. So of course this is based on the speed of light, and now I don't know how they have okay, no. So basically this change defines the speed of light to be so much meters per second, so many meters per second. Now the kilogram, the SI unit for mass is the kilogram, abbreviated as kg. It is defined to be the mass of a platinum iridium cylinder kept with the old meter standard at the International Bureau of Weights and Measures near Paris. Exact replicas of the standard kilogram are also kept at the United States National Institute of Standards and Technology, or NIST, located in Gaithersburg. If I'm pronouncing that right, I'm not familiar with the place or the name. Maryland, outside of Washington, D.C., and at other locations around the world. The determination of all other masses can be ultimately traced to a comparison with the standard mass. And so this is basically the meter. Light travels a distance of 1 meter in approximately 300 millionth of a second. So the meter is defined to be the distance light travels in 1/300 millionth of a second in vacuum, and distance traveled is speed multiplied by time. So electric current and its accompanying unit, the ampere, will be introduced in Introduction to Electric Current, Resistance, and Ohm's Law when electricity and magnetism are covered. The initial modules in this textbook are concerned with mechanics, fluids, heat, and waves. And in these subjects, all pertinent physical quantities can be expressed in terms of the fundamental units of length, mass, and time. Now, the next thing that we have here is the metric prefixes. And I think if we need to end this video here, because this is going to take some time and I'm already at 53 minutes. So I'll end this video here and then we will continue in the next video. Thank you.